I can't.
Let's begin. So yeah, we are going to go over problem set 2, which you guys worked on in groups, just to make sure that we actually did these things the correct way. Okay, so 1A, everyone was supposed to do 1B. 1A is what we actually did in class 4. So we had a rare disease that 1 in 10,000 in the population have, which basically was them telling you the probability of having the disease is 1 in 10,000. And you believe you have the disease, you get tested, and it comes back positive. Doctor says it gives a false positive in 1% of cases, which means the probability that you will test positive, given that you do not have the disease, is going to be 1%. But there's a chance of 99%. There's a 99% chance that if you have the disease, it will correctly identify you. So the positive, given that you have the disease, is 99%. And we had to figure out what is the probability that you actually had the disease, given that you got this positive result. And basically we used Bayes' theorem. So this is just a repeat of what we actually did in class, so that when we move on to part B, you can see what we're doing. By Bayes' theorem, we realized the chance that you actually have the disease, given that you had a positive result, is going to be the probability that you got a positive result, given that you have the disease, times the probability of having the disease over the same thing, plus the opposite. What is the probability that you will get a positive result, given that you don't have the disease, times the probability that you don't have the disease? Because you may or may not have the disease, and this will be the sample set for the general population, the sample size, or probability based on the sample size. So we went and we plugged in all of these guys, and we had 0.01 times over chances that you will be positive that you don't have the disease, 0.01 times here would be 0.9999. It's 4 nines, right? And then we calculated that, and we got, what was it?
0.009.
Right, 0.98% chance, right? Which was a 1% chance, which might seem surprising until you think about it. Most people, especially those who haven't taken probability, will probably guess, well, if you got a positive result, there's a 99% chance you have the disease. No, it's actually a 1% chance. And the idea here is that you have to actually remember what are the chances of having the disease in the first place. Sometimes we kind of zone in on the wrong facts, and it kind of colors our judgment, and Bayes keeps us honest. Now, in part B, the same guy wants to get a second opinion, right? So it's not good enough for him that he has a 1% chance. So in part B, which is what everyone was supposed to do, you get tested a second time. Go to a different lab, a different doctor, everything brand new, and you get another positive result. How do you know what is the probability of having the disease now? Yeah.
I've seen different sample space. I've seen the probability of anybody getting it, because now you have to consider if people are already testing positive.
Okay.
So with a 1 over 10,000 one for P and D, you now put the 0.98%.
Right. So this was if we didn't know anything about the guy walking into our office. We have to make a guess. What are the chances that this guy actually has the disease? Well, it's prevalence is 1 in 10,000, so that would be the guess. However, this guy has updated information, right? Whenever information is revealed, it changes the probability. So for this particular guy, he is now not here, he is now here. So now, what is the chances that he has the disease giving a positive result? In fact, a positive result, which is going to be the second one. With that updated information, now we have to talk about, well, the probability around this test isn't going to change. So that's going to still be 0.01, but now instead of this, we have to plug in this. And then that's going to be 0.01 times that, plus this is still going to be the same thing because the test didn't change, only the individual changed. But now this part is going to be 1 minus that, right? So it's going to be 1 minus 0.0098.
Wait, Jhevon, should
Yes.
see 0.99 there?
Yeah. 0.99.
Like you plugged in the wrong
Like
number.
next to the
Next to the 098.
00,
Yeah.
01 and the 0098, shouldn't it be 0.99?
No, the first part. In part A.
I'm kind of plugging in the same order here.
No, but you plugged
Well,
in the
up
wrong
there.
number.
This,
Yeah, look.
yes, so that would also be incorrect since thank God Nick is paying attention.
It was Rosie.
It was me.
It was Rosie.
Okay,
I just
so
told
Nick
him,
is
so he
trying
could
to.
tell you.
He's also honest.
He saved it. I was just gonna be like, Nick is trying to steal this thunder, but now he's honest. So God. Okay, you're both paying attention. You're both good. Okay, so that's gonna be here. Right, and so that would be what the updated probability is. And what was this?
49.5.
49.
0.5.
49.5%. Now his probability is higher. Now there's something that you can kind of guess what would be happening here. Let's say he went to another doctor and got tested again. What do you expect to happen to the probability? You get higher. And again he gets a positive. And again, what's going to happen is his probability of actually having the disease after having a bunch of positive results, it's actually going to inch closer and closer to 99%. Eventually he's going to have to face the music. Dude, more than likely you got this thing, right? One more positive result is going to push him beyond the 50% mark, which means he's more likely than not to have the disease. But this, one reason why I wanted to do these two parts is I wanted to kind of show you how Bayes is actually used in the real world. Because we know that probabilities get updated upon new information, this Bayes formula is really meant to be used in reiteration purposes, right? So there are times when you might not know a certain probability, right? For example, the probability that this guy that walked into the office has the disease. But you know the chances of some other thing based on some statistics somewhere else, like from the CDC or whatever, and lab results on this test. So you know some probabilities, but you don't know a particular one. So what you can do is you can use Bayes' theorem to kind of estimate what's going to happen. And every time you do this, you can update a probability and hence update your chances of something else happening. And so Bayes is really important in that it tells us how to actually update our beliefs about what the chances of something actually occurring is. And in fact, Bayes himself used his own formula in this way. He never really used this formula as a one-off. He kind of used it in repetitive fashion to kind of update his probabilities on certain things. And yeah, so this is something that is a common misconception. And whenever someone makes a mistake that is kind of like this, we say that they've fallen into the Bayesian trap. So there are many other examples that you could give. Another common type, the disease example is a very common example. Another type is when you have to guess that a certain person is within a certain group. So, for example, you meet someone on campus and they happen to be a very shy person, you know, they're very kind of quiet. And you know, from interacting with this person, you realize that they were shy. And if someone were to ask you in that moment, okay, you have two options. You were to guess what this person is what this person's major is, and you have the options of, well, is it more likely that they're a math student or a business student in marketing or something? You know, given that the fact that you know that they're shy. And a lot of people will kind of reason like this, well, you know what? They're more likely to be shy if they're a math person, to be honest. I mean, business people, they're all about, you know, interacting. And, you know, math people, they're stuck in the basement, you know, just doing calculations on their own, you know, not having any friends, you know. I don't want to go out to the party. I want to solve this probability problem. Like, that's not. So you're like, okay, so if I were to guess, I'd probably guess that this person was a math person. And it turns out that would be a trap, right? That's because you are focusing on the wrong probability. You're focusing on the fact that you expect most math people to be shy versus what is the actual prevalence of math majors versus business majors, right? That's going to be important, right? How many math majors are there for each business major? I mean, come on. I have classes with math, they're not this big, right? Every time I have a business calculus class, it's huge, it's almost 30 people. When I have like a class with math majors, like 15, 20 people, and not even all of them are math majors, they're probably like chemistry or something. Like, math majors are rare in general, right? It's kind of like the probability of having a disease. But the probability of you bumping into a math person is like the probability of like 1 in 10,000 people, come on. So when you have a lot of business people, even if it's a small percentage of them that are shy, that number of people is going to be larger than the large percentage of the math majors that are shy. You understand what I'm saying? So it's like, let's say you have 10 math majors. For every, I'm just making up numbers here just to illustrate the point, for every 100 business majors. And let's say, you know what, shyness is really common among math people. Let's say 90% of math people are shy. But only a few business majors are shy. Let's say 20, 25%. So shyness is not something that's commonly associated with these guys, but it is commonly associated with these guys. But then when you kind of look at the numbers, this over here would be 9 people who are shy. Whereas over here, there would be 20 people who are shy. So if you were to group all the shy people, which is what your sample space should be, you would have 29 people. And guess what? You're twice as likely to bump into a shy business person as you are a shy math person, right? So normally, just because a lot of people will focus on this and completely mess up how they think about things. And a lot of our judgments fall into this kind of thing, the Bayesian trap. We just have some prior belief or bias that we have, and we kind of make our judgments based on those things without really understanding what was the thing that came before that. What is the prior set of statistics, right? Bayes' theorem is what helps us not forget this, right? So you need to check your biases sometimes. There are a lot of times where you'll make certain guesses based on certain facts that you know, and you totally make the wrong guess because, you know, there are facts that are one level above that you're not considering. There's a good book, Thinking Fast and Slow by Daniel Kahneman, where he also does he's a psychologist and he studies biases and, you know, logical fallacies and things like that. And he also mentioned that people often make this fallacy. And he did a very similar example with, I think he was farmers and librarians, right? Like, you meet a shy person, are they more likely to be a farmer or a librarian? Most people are like, librarians are, you know, often shy. And, they speak quietly. And no, like, there are way more farmers than librarians in the United States. You're actually way more likely to meet a shy farmer than you're a shy librarian. So that was kind of the upshot of Bayes' theorem. It tells us how to update our beliefs, and it kind of saves us from our own biases. So just keep that in mind. Every time you meet someone and some previous bias causes you to make a judgment about them, or a situation, you make some previous judgment, then you have to, oh, wait, hold on. I know I believe this, but what is really the numbers in the background here? And maybe I can actually have a better chance, make better decisions. So that's what base theorem is about. It's a very useful rule. It's one of the, probability has a lot of really great applications, but base theorem in particular, we apply that all the time. Let's do problem 2. So this was on our probability teasers page. It was the birthday problem. Was it this class that we actually did the birthday thing in front of?
Yeah, we didn't go over like how to do it.
Yes.
No, like, I mean, did we say the birthdays? I didn't. Like, no, we didn't.
Let's
You
do
wanna
it
show
now.
it right now?
It was true in the other class. Like, we actually found 2 people with the same birthday.
No
We
way.
did. We did.
Can we do
Right
it?
now?
Wait, you want to do
Can
it?
we actually?
I don't know. Well, okay.
Go. November 17th.
No.
March 28th. January 21st.
October 10th.
28.
November 7th.
November 7th. Oh, that was yesterday.
What?
Oh.
Happy belated!
April 9th.
April 9th.
March 27th.
December 20th.
He said March, you got excited.
April 12th,
No,
October 18th.
no,
August 31st.
no,
November 10th.
no.
June 16th.
What?
June 16th.
June 16th. No,
June 29th.
no.
October 19th.
October 19th. Hey, yeah, we got one. Yeah. Like, about 51% of the time I do that experiment, you'd actually find me in the room of 23. So here we have 20, I think there are 27 people in this class. So yeah, I was actually like a little more than half the
Hold on,
time
we didn't get to
we'd
say on
actually
March, I
find
think.
that. Let's actually find the probability. How do I know that I only need 23 people?
He was like, fuck everyone else.
So there are 23 people in a room. What is the probability that at least 2 will share the same birthday? Okay, so for this, just assume a year has 365 days. How did we actually do that? 23 people in a room. Probability at least 2
I just saw them.
has the same birthday. How did we actually do this? The group that did this. What did you try?
Hey, when's Jhevon's birthday?
Huh? Huh?
When's your birthday?
November 6th.
What? No, 2 days ago. We had class on your birthday and you didn't
I
tell
should be born, yeah.
us. We would have bought you a cake and everything.
What?
Yeah.
What?
I would have bought you a cake.
How did we actually do this? Yeah.
So we found what 23 choose 2 was, and that's 253.
Okay.
And then we took 364 divided by 365, and that was like a long decimal, which is 0.9.
So you took 22.
23 choose 2.
Okay.
And then 364 or 365.
That was 253.
This is 253. And then
364 over 365, which was 0.997.
okay. And then what did you do with those 2 numbers?
We put 364 over 365 to the 253rd power.
Explain the reason. Why would you do this?
So those are the chances that they don't have the same birthday. So if you subtract that from 1, that would be the chances that they do have the same birthday.
Why is this a chance that they don't have the same birthday?
Because it's only 1 day out of the year, so there's 364 other days that they don't have the same birthday.
Yeah, but what if the same birthday happens in one of the other 364 days? You know what I mean? Like you just single out 1 day that they all can't have the same birthday. But there were like a lot of days.
In the 253, we thought represented like the amount of possibilities that they share the same day. That's why we raised it to that. So we thought like it might not be right, but we thought 364 over 365, there's the probability that like one person doesn't share it with anyone else, then we raise that to the number of possibilities that they didn't.
Oh, but that wouldn't be correct. 364 or 365 is the probability that one person doesn't share the same birthday with one other person. Right? If you find the birthday of one other person, okay, so that's one of the 365 days. You pick another person, what's the probability that he doesn't have the same birthday as that guy?
So should we have
It's
done like
this.
342 over 365?
No, you should have kept going with this reason. What you can, well, that's how I would probably do it. It's 1 minus the probability that no one has the same birthday. So first is to realize that that's the complement here. Now, how would that actually occur? Well, you go kind of think in stages. That's probably how I would do it. And I'll just do the probabilities here. So this is the first person, second person, third person. You kind of line them up. Kind of what I just did with the class actually. Like, first person, what's your birthday? Second person, what's your birthday? Third person, what's your birthday? And I just went and I kept updating the probability. So let's say I did that ... 23 times. What would have to happen for them not to have the same birthday? Well, the first person can choose any of the 365 out of the 365 days. He has no restrictions. The second person, though, has to say a different day, right? So he'll have 364 options out of the 365. The next person only has 363 options out of the 365. The third person, 362 options out of the 365. And so on and so forth. And what the top is going to go down to what? 365 minus 23 plus 1. So 365, what is that? 366 minus 23? Huh? That's 3 what? 343 is where it would stop out of 365. That will be the probability. Notice that in the denominator you have 365. And by the way, I can multiply the probabilities because we have independence here.
Wait, Jhevon, why do we add 1?
Yeah.
Why is it 343, not 342?
Oh, because we saw that if you have n times n minus 1 times n minus 2. Remember the last thing, if you're choosing m, it's n minus n plus 1. It was actually, you can think of it as p n n. Right? So, for example, notice that if you had 6 and you're choosing 3, so that would be you have 6 times 5 times 4. So the 4 is actually going to be the 3 plus 1. That's where the plus 1 comes. Because the first guy is actually counted. So we have that. So notice that this will actually give us the probability of 365 choose 23. In order, because I put them in order to figure this out. Over 365 raised to the 23. That's going to be the chances. What's that?
So you can multiply these because they're independent.
Yes. So there's a probability that the first person was not born on the same day with the second, and the third, and the fourth, and the fifth, and the sixth. There's a way to do it without assuming independence, and it will look pretty much the same, actually. But you'll do conditions. What is that number? What is this?
49. Yes.
Come again?
0.4927.
4927. Okay, so we needed over, the birthday problem was over 23. I think one more will push you into like 51%-ish. Yes. you have a question?
No, I don't.
What is the probability that someone will not have your birthday? Well, you're pretty much going to do the same thing, except you are now looking at you're singling yourself out, and you're looking at 22 people.
You just start from the second spot and do 22, choose one.
Yes, so similarly.
Jhevon,
Yes.
for the last problem, why do you use pick instead of choose?
Because the way I thought about it, and this, like I said, this is how you want to make sure you're setting up the problem. The way I thought about it is putting people in order
So
and asking them. Yeah, so that's how I conceptualize the problem. So I asked the first one, what's your birthday? Second, third, fourth. That was how I was thinking about it. And so, and when it looks like this, I realized, oh, a permutation almost looks like that. So I can use that formula. Yes.
I was just curious, so once you solve the probability of the 365 to the power, do you subtract that number from it? Or is that the full answer right
Yeah, no, just subtract that one, that's how you get 51%.
there?
Oh, we didn't do that? Oh, sorry, yes. I forgot the subtracted one. 1 minus the probability of the 365, choose 23, and out of the 365, raise to 23. And that would just be that's 1 minus the 0.49, which gives us what?
50.7.
507. So it's like a 50.7% chance. So it's a little bit more than half. Right. So it was 23, not 23. Forgot the minus 1. So it's likely that two people have the same birthday. Similarly, if you single yourself out, which means now you're choosing 22 people. So similarly, probability
We were close.
someone has your birthday is going to be 1 minus the probability no one has your birthday. It's going to be 1 minus. Now you're only thinking about, you're only counting the 22 people, right? Because you single yourself out of the 23. So there's going to be 365 to the 22nd power. And the probability is they now get to choose from 364 days, and you're picking 22 people. And what's that? So you kind of single yourself out and you line up the other 22 people. So once you kind of worked hard to figure out this was the answer for that, you just tweak that answer for this one. What is that going to be here? What is it?
Yeah.
Point.
That point
Yeah, 0.4927 again.
Yeah, same answer.
4927 was what we got before.
Yeah.
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 I think the decimal after
Yeah, it's the same answer.
I mean, it's going to be close, but I don't know.
No, it's like the same exact answer.
Should it be, why is it 365?
Yeah, it should be 360.
Why is it 365 again?
So you single yourself out, so you put, this is,
Would it be 364?
yeah.
How would you-
Yeah, for that it's really 47.6%.
It's 0.47.
Yeah.
What else?
6.4.
Okay, and what's that?
Yeah, I subtracted the one already.
That's with the
That's-
ones
that's-
already
That's with the
subtracted.
one
Yeah.
subtracted, okay. So, yeah, so there's a 47% chance. So if I'm looking at a group of 23 people, I wonder if 2 of them have the same birthday. There's actually a 51% chance of that. If you're a member of the group and you're wondering, I wonder if any of these other 22 people have my birthday, there's actually a 47% chance. And now in both my classes it was actually true, so it's a 100% chance, right? I'd have to do it over and over. Bayes' theorem would tell me that I don't.
Does that mean like if you like talk to a friend and you know their birthday and your birthday, like it's gonna keep going down? It's like the more birthdays you know, like
Yeah, the more birthdays you know, the lower chances. If you know a bunch of birthdays and you already know they're not the same,
yeah.
then the chances of someone else in the other group having the same birthday goes lower. Yeah, every time. 3, I'm interested in, what did you do with this one? On a table there are 5 coins, but 2 of them are unfair. 2 of them are like two-face. This coin. They're double-headed. So yeah, on the table you have 5 coins. 2 of them have double heads while the rest of them are normal. You pick a coin at random, you flip it. What is the probability that the coin shows heads? I don't know what group did this, but what did you try?
So we thought about it as like 2 stages. First, you know whether or not you're going to pick up like a two-face coin.
Okay.
So like we drew a tree diagram.
Tree diagram.
Where
Okay.
one of the options is here in the 2-face probability.
So the fair coin, you could have picked the fair coin versus the unfair coin.
Right. So with the fair coin, there's 3 out of 5 are the fair coins, so 3 flips, and the unfair coin is 2 flips.
Okay. Now if you pick the fair coin,
There's 2 more possibilities because you flip it. There's a 50% chance of heads and 50% of tails. And then the unfair coin is going to be 10% right. So
yeah, there's a 1%, a 100% chance that you'll get heads in that situation. Okay, so how do you actually calculate the probability?
So because they're independent, you can multiply. So 3 this times a half, 3 this times a half, you get you. Right.
Not necessarily independent. Here you kind of have to think in terms of conditionals. Because the chances of you getting the heads is actually dependent on which coin you actually pick. So what here you want to think of this is the probability of picking the fair coin. This is the probability of picking the unfair coin. And this is the probability of getting heads given that you pick the fair coin. This is the probability of you getting tails given that you pick the fair coin. This is the probability of you getting heads given that you pick the unfair coin. So technically here we are going to be using conditionals. So probability of getting heads is what are the chances that you'll get heads given that you chose the unfair coin times the probability that you chose the unfair coin plus the probability that you will get heads given that you chose the fair coin times the probability that you chose the fair coin. What you'll notice that what this tree diagram is actually telling you is Bayes' theorem version 1. Unofficial. So this, by the way, is, so using this, we often call it using this is solving probabilities by conditioning. So first he set up some conditions. Well, the chance of you get heads, well, it's based on the condition of whether you got the fair coin or the unfair coin. So yes, the tree diagram idea still works, you multiply along it, but don't make the mistake of thinking that alone implies independence, because you're actually getting that here. So ultimately, you get the same answer, but I want to make sure you're thinking about it the right way. This would end up being, probability of picking the unfair coin is 2/5. The chance of getting heads if I pick that is 1. Plus the probability of picking a fair coin is 3/5. Chances of me getting heads if I pick that is 1/2. So this is going to be 2/5 plus 3/10, which is, this is 4/10 plus 3/10. 7/10. So you can think of it as a tree diagram, multiply along the arms, realize that you want this arm plus that arm, because that's all the ways you can get h. You could also think of it in terms of the formula, base theorem version 1. You could also, I think, set it up as a sample space about coordinates. Ultimately, you'll realize that you have how many h's versus t's? Right, so basically for 5 coins, you would have 10 sides. And you can count the number of sides that would be tails, the number of sides that would be heads, and you can do it that way as well. What happened?
We did that first. It seemed too simple.
Yeah, no, that's actually fine to think of it that way. Tell you, as long as you have like a scheme in your mind for how to do it, like a valid scheme, you would have multiple ways to get to a problem. Just make sure you're doing it a legal way, and you won't get in trouble. So you could have done it that way. So you can think of the sample space as like the first coin, the second coin, third coin, how many pair was there? 3? Now the fourth coin, let's say that was unfair, you get 2 h's. And the fifth coin that was unfair, you get 2 h's. 1, 2, 3, 4, 5, 6, 7. Ultimately, you'll notice that here there are 7 h's. And 1, 2, 3 t's. So you also have 10 total possibilities. So these aren't all equally likely, so it's not gonna, we can't take the size of the sample space. And we are looking for 7. So the sample space idea was a little bit risky here because there is the idea of you can probably pick 1, 2, 3, 4, 5 out of the sample space, but these aren't equally likely because the double-headed thing kind of messes up the weight. This one will have a higher weight than the other 3, so you need to be aware of that. Get through one more. I mean, we'll do all of them ultimately. And next time when we do problem 7, that's a whole new kind of probability. Let's get through problem 4. A bowl contains 10 balls. 5 are red, 4 are blue, 1 is green. You select 2 balls at random. You replace the first selected ball before picking the second. What is the probability that both balls are green? So where 5 are red, 4 are blue, 1 is green. Select 2, probability. So A, probability both green. How did we do that?
So, I thought of it in stages.
Okay.
So the probability that you pick the first one green is 1/10,
Yeah.
and then
Probability that the first green times probability that the second is green.
yeah, and since you're replacing it after you take the first one out, it's
Yeah.
1/10 for both.
So you have 1/10 times 1/10. There's a 1% chance that both are green. I want you to notice here we have independence.
Yeah.
Because you're replacing it, your first choice actually has no effect on your second choice. And I guess once you figure out that kind of reasoning, the others will kind of fall into place easily. The probability that both blue can think of this as the probability that the first is blue times probability that the second is blue, because you have independence here. It's 4 out of 10 times 4 out of 10. 16% chance of that happening. How did you do both the same color?
So we figured out the probability of them being both red, them being both blue, them being both green.
So probably of both red
Yeah.
is 5 out of 10. 5 out of 10. There's a 25% chance that you pick 2 reds.
Yeah, and we have blue, 6 blue.
So the probability of same color is probability both green plus probability of both blue plus probability of both red. And we add these because it's OR and mutually exclusive. Notice that these cannot happen at the same time. You can't have 2 greens and 2 blues. That would mean you chose 4, right? So you're either going to have 2 greens, or in a completely different scenario, different universe, 2 blues or 2 reds. These do not overlap, so we can add the probabilities for the OR, and that's going to be the 1 over 100 plus the 16 over 100 plus the 25 over 100. So what percentage chance is that?
That was 42%.
42. There's a 42% chance of that happening. Both different color.
The opposites.
The opposite. That's the complement of that. So for D, probability of different color, 1 minus the probability of the same color. 88% chance. We'll do the next 3 problems next time, and problem 7 is going to give me an excuse to introduce a very important idea. So stop there.
All right, take care.